Hello everyone, I'm Nikita Tarakanov. First of all, I want to say that it's a great honor to me to give a talk at Hack in the Box, second time in a row. And today I'm going to talk about exploiting previously unexploitable pool corruption in Microsoft Windows kernel. First slide about me. On Twitter page I have several aliases like Crazy Wild Russian, Line of Stars, but basically I'm just a nice dude. And I'm homeless independent security researcher from Russia. Now, I have kind of Russian special sense of humor. Okay, basically we're gonna talk a little bit about previous research, then to be disclosed it's a new approach, and in the end I will talk about some conclusion and question and answer section. At the moment, exploitation world goes in the direction when major vendors make situation when you have to have a lot of combination of vulnerabilities to compromise bugs. For example, Google Chrome, there is a sandbox. Internet Explorer, there is a sandbox. So first of all, you have to bypass SLR, DEP, and then escape sandbox. Actually, Microsoft Windows kernel hasn't functionality to build great sandbox. For example, GDI is a good vector for attack from a sandbox. Good example on last point to own, Niels and John from MWR Labs found Google Chrome using vulnerability in WebKit, and next they attack Windows kernel. So basically, they didn't attack Chrome sandbox, they just bypass it using some vulnerability. I think at the moment there is no info about in which exact component of Windows. Is it in Win32k.c, so is it in NTOS kernel itself? But they tweeted that they exploited kernel pool overflow in Windows kernel. So there is they popped up calculator with system token. So from untrusted, from sandbox process, they gained full compromise. So I think it's cool. I make some statistic research, and from 2008 year, I can say that most of the local privilege escalation, most of the vulnerabilities in Microsoft kernel are memory corruptions, and there are just a little bit of stack overflows. Most of them are pool corruptions. And that's why Microsoft enhances security of pool allocator. It starts from, Microsoft started from Windows 7, because till Windows 7, pool allocator was pretty vulnerable to easiest attack. And in Windows 8, pool allocator is kind of bulletproof, but there are still attacks again. So there is a really good research out there about pool allocator mechanisms, and in my opinion, the most comprehensive one is by Taji Mand. And by the way, I was in Black Hat in March, and Zhenhua Eric Liu talked about some nice techniques to manipulate heap and pool very precisely to make pool to appropriate state for exploitation on Windows 8. So we start with some basics. Basically, kernel pool is just a heap but in kernel land. I'm curious why Microsoft calls it pool. Actually, it's heap, but okay, pool. The major difference between userland heap that there are different types of memories. There are non-paged pool, paged pool, session pool, and each pool described by structure. There are stored and defined in tuple vector array. So here's just output from debugger. There are a lot of fields in the descriptor of pool, but the most interesting one are list heads and pending freeze. So list heads is just an array of double linked lists of free chunks of the same size. Because there is 512 entries, and the granularity is 8 bytes, so list heads store chunks from 8 bytes to close to page size is 4080 bytes. So to describe allocated memory, there is a pool header structure, and there is a fields which previous size, pool index, block size, pool type, pool tag. They describe just the size of current of previous chunks. Also, pool index stores index of pool where the chunk resides. Actually, pool header on 32 bits and 64 bits not the same, but the only difference is that on 64 bits there is a pointer to process, and because it's 64 bits, granularity a little bit bigger. So if on 32 bits operating system granularity is 8 bytes, on 64 bits operating system granularity is 16. So when a chunk is freed after the pool header, there's a list entry. Basically, it's just structure that stores a pointer to forward chunk, to forward free chunk, and to backward. So this is how it looks like in graphic mode. Basically, because kernel pool was made, there are a lot of algorithms, and for small allocations, there is a different list called the leukocyte. And for small allocations, there is a there are leukocyte lists, and they stored and defined in process control block. And the maximum size is 256 bytes. So, and there is change. There is a single list. Leukocyte is a single list, and list heads are double linked lists. So in graphic, you see that there is only pointer to next one. So there is no pointer to backward chunk. So for great allocations that bigger than page size, there is a mechanisms for allocating pages, and there is a special. I think it was done for performance reasons. If there are lists for 1-page allocation, 2-page and 3-page. If bigger allocation is requested, there is a bitmap which describes which page is allocated, which is free, and so on. So basically, there are a lot of functions to allocate memory in kernel land, but in the end, they all invoke xallocate pool with stack. So it's kind of one and only interface of allocating memory. And the basic algorithm returns new chunk. Firstly, it looks for leukocyte list, then list heads, and pool page allocator. By the way, for example, in some manipulation techniques, there is a technique to store a lot of chunks in leukocyte lists, and allocation algorithm works in this way. If leukocyte lists are full, it returns a free chunk from list heads. So this is just the order of allocation. Then one of the key points of this research is that kernel pool allocator allocates first chunk at the top, and secondary and following allocation from the bottom. And the chunk header of first allocation has previous size, which is 0. It will result in some cool stuff, which I will disclose a little bit later. So when you have to free some memory, there is also a lot of functions to free, but in the end they call xFree pool with tag. And basically xFree pool with tag returns chunk header to appropriate list. And there is also one of the key points of techniques that if adjacent blocks are also free, allocator merge, also it's called coalescence, free chunks to reduce fragmentation. So, for example, in this situation, if there is a free chunk, next is busy, and next is also free. When you free busy chunk, allocation algorithm looks if adjacent blocks are also free, and allocation algorithm merges it to bigger and bigger. So in the end, we get just one big free chunk. So talking about previous research, there are first one is from XCon conference in 2005. Next was in CSCAN, the most comprehensive, in my opinion, from Tarjimant, and the newest one at Black Hat. Actually, you know, I'm really curious because each research is focused on attacking pool allocator itself. And for example, after Tarjimant at the Black Hat DC talked about some cool flaws, about cool attacks versus allocator on Windows 7, Microsoft security engineers from Microsoft, I think they read his slides and they just simply eliminated all his techniques. And in the 2012, he discovered just 2 more techniques. So pool allocator is really, at the moment, kind of bulletproof. So talking about early days, before Windows 7, it was in 2008, research made by Kostya Karczynski was about creating fake entries, and it leads to write 4 primitive or write 8 primitive when you control pointer and when you control data. So there is several scenarios. I just show one. So basically, it based on how entry is removed from double linked list. So if you control some entry, it turns that you control overwrite of arbitrary memory. So basically, in kernel, it results in a compromise. So this is an example of exploiting using fake entry. So if there is a chunk, there is an overflow, there is a next header, and we change header of next chunk, we change, for example, previous size or block size, and it results that pool allocator thinks that there is also fake header, which actually we constructed, and it turns that when the next header is freed, there is a merge, and we get write 4 primitives. So we can overwrite arbitrary memory, which is full bunch. So these techniques, they're about variations of that technique. And in Windows 7, this technique was partially eliminated because in Windows 7, Microsoft implemented safe unlinking. In 2011, Tadji discovered that Microsoft implemented safe unlinking in not so secure way. There are about 5 techniques. For example, list entry of link override, he discovered that Microsoft checks only backward link. So if you control forward link, it leads to arbitrary pull override. Next, there are some techniques from him, but I'm not gonna describe them. You can check his slides. I want to say that all these techniques lead to write 4 primitive, and they attack pool allocator metadata. So, for example, pool index override, there is a technique to override index, and it leads to pool index out of bounds condition and write 4 primitive in the end. So Microsoft security engineers from Microsoft have done a really great job in Windows 8. There are a lot of mitigations, and they basically, I hope they read his slides and eliminated all previous techniques. So Tadji made a great job on Windows 8 and discovered just a little bit more techniques. For example, block size attack. If we have a vulnerability whereas we control overflown data very precisely, we can overwrite block size to bigger value, for example. And as I told before, there is some a trick if we overwrite chunk header at the bottom of the page. There are no checks of some metadata, for example, block size and previous size. So basically, I can show it on graphical mode. So for example, we have 4 chunks that fill the page, and there is an overflow. We change a block size of chunk header to fill it to the rest of the page and free it. So basically, we fool pool allocator that he thinks that there is no chunk here. And when we allocate bigger size, it returns bigger chunk. And for example, we can reallocate this freed memory by something which is controllable, like Unicode strings. And it turns that we overwrite content of this chunk. So basically, it leads to arbitrary memory corruption. So why I talking here? Because to attack kernel pool allocator with, for example, this technique, by the way, split chunk attack, it's kind of variation of block size attack. So I just skip it. To exploit such vulnerabilities, you have to have almost full control over overflown data. And my experience shows that there are a lot of vulnerabilities when you haven't control of overflown data, or whereas overflown data is constant. So you haven't a chance to construct a fake pool header with bigger block size, so it doesn't work simply. And basically, all research about exploitation pool corruptions is about describing some tricks in pool allocation, in pool allocator mechanism, and so on. So, and on Windows 8, it's very hard to exploit some vulnerabilities in a reliable way. So, you know, I dissect vulnerabilities, pool corruptions, in two groups, which are sweet, which you can exploit using public techniques like of Targi or techniques by Costa, and there are hardcore vulnerabilities. And you simply haven't chance to exploit hardcore vulnerabilities using public techniques. So, just examples. I have discovered a lot of vulnerabilities with these types when overflowing data is uncontrolled, or there is a mem set with zeros or with some constant, and there is no way to construct a fake header in a correct way to apply some of the public techniques. So I was thinking about, I imagined a situation, what if pool allocator is bulletproof? What if there is no attack, there is no technique against metadata? So what if current pool allocator is totally bulletproof? Basically, this technique came from userland, because in userland, nowadays, exploit writers use contents of memory. For example, how exploit writers bypass ASLR these days. They use objects, so they overwrite content of some JavaScript and so on object. And I was researching, so what we can overwrite in kernel. Of course, kernel has objects. For example, registry objects, file objects, LPC, ALPC, semaphore objects. There are a lot of types. So to describe objects, there are headers, and there is an object manager in Windows, which is kind of big part of Windows kernel itself. And basically, this technique is based on direct kernel object manipulation, which is known for a long time, but in rootkit world, not in exploitation. So actually, I'm curious why at the moment there is no research using rootkit techniques in exploitation field. So there is a definition of object header from WRK to show you the most interesting ones. So there are types of objects. Basically, when you allocate kernel objects, after chunk header, so after metadata of pool allocator, there is object header, and after object header, there is a body, so actual contents of objects. This structure changed a little bit since Windows Vista, but it just there is a pointer to type, and on Windows 8, on Windows Vista, on Windows 7, there is an index to array of object types elements. So object type describes some things, but the most interesting one is object type initializer structure, which holds pointers. And yeah, I just show that on different operating systems. Basically, object manager is the same since NT 4 till Windows 8. I mean, algorithms. There are a lot of new objects in the Windows Vista and Windows 7 and Windows 8, but algorithm structures are pretty same. There are just a little bit changes between newest versions. So object type initializer structure holds pointers to procedures. For example, for open object, for deleting object, for parsing, blah, blah, blah. There is an example, just they look same. They look same. There is an example of LPC object type. So there is pointers to some functions like open procedures is LPC open port, close procedure is LPC close port, and so on. So the funny thing is that array that holds pointers to object type elements starts from the third. So first element and second element are kind of magic. First element is 0, and second element is has value Bedo Bobo, which is my magic value at the moment. And on 64 bits operating system, these constants are extended by zeros. So on 64 bits operating system, second element resides in userland address space. So how we can use it in exploitation? We can smash object header, call special syscall, which triggers actually the sum of the procedures, and this leads to hijack of control flow. So we gain just control of EIP or RIP register. So in steps, first of all, we spray pool with objects, depending on what vulnerability we exploit. For example, if it's not paged pool, we spray objects that allocated in non-paged. If paged, we use objects that allocated in paged pool. Then we fragment, also massaging, feng shuing pool. Basically, we make holes at the bottom of the page. It's to predict where allocation will take place. Then we trigger actually vulnerability, overflow, corruption, because we make holes at the bottom of the page. When overflown chunk is freed, there will be no blue screen of death, because there are no checks of metadata. So we can free overflown chunk and work next, call syscalls, whatever. So basically, there are a lot of procedures like open, dump, close, query security, blah, blah, blah. But funny thing, I discovered that there is one special system call, because in the name there is a security, anti-query security objects, but in fact it turns that we gain control of a EIP register, so it's not so secure. Basically, when we overflow object header and next call this system call, after object reference object by handle, we get memory of pointer to memory where the object is located, because header is located before object, so there is a minus. Here's a YAX, actually it's type index value, then it dereference, and in the end we get call EDX. So we get control of EIP or RIP. So all these techniques are based on this array, because this array holds information about all kernel object types. So, and in this array there are some interesting things. Basically, index is 1 byte, but if you can see, there are object types, and this array has 0 values. So if you overflow type index with some value which is out of bounds of this array, you can get null pointer dereference. And by calling anti-query security object, you gain control of execution flow. But the thing is, as you know, on Windows 7 you can't allocate Windows 8. So this technique, using out of bounds, using 0 null values, it works till Windows 8. But actually, I woke up today and see picture that Microsoft backported this restriction from Windows 8 to Windows 7. So basically, Microsoft eliminated this technique. But I'm not mad, actually, because there is a special value, which is bad bobo, and it locates at second value in array. Basically, this magic constant is from NT4 till leaked version of Windows Blue. I checked kernel of leaked version of Windows Blue, and this code is still there. So actually, I don't know why Microsoft chose this constant, because you can spray memory to achieve this address. I don't know why. And on 64-bit operating systems, situation is even worse, because this constant extended by zeros, and you simply can allocate memory, allocate in user land, make fake object type entry, and gain execution. But on the other hand, I hope Microsoft will implement SMAP in Windows Blue. SMAP will eliminate this technique on 64 bits, but on 32 bits it will still work, because SMAP will not help if memory is in kernel. So this is just a disassemble of a function. So basically there is just one prerequisite to apply this technique. You have to have value 1 in overflown data. And you smash type index with value 1, which is kind of special, bobo, spray memory, and gain code execution. So what if you haven't this value in overflown data? So you have to find another solution. And for example, security procedures of different objects are different. So for example, for file, the security procedure is IOP get security object. Of registry key, it's the CMP security method. And basically, we can full kernel, we can overwrite type index of registry key to file. And this will lead to some vulnerabilities, some of memory corruptions in legitimate code. So, because CMP security method thinks that it dispatches registry object, but we can forge their fake object. And so object type confusion, we can change type and date of kernel object. This will lead to redirect of execution flow, and we can achieve write for primitive. But object type confusion has prerequisites that to achieve that we have good control over our flow and data, because in functions that dispatch kernel objects are big structures with a lot of fields, and in some situation, for example, if we smash some fields of object with zeros, there will be null pointer dereference, and there will be blue screen of death. So it's kind of a hard technique to implement. So basically, Microsoft, totally forgot about another vector. Microsoft enhances pool allocator mechanisms, but totally forgot about object managers, object headers, and there is no security checks. There is no cookie in object header, but kind of SMAP will eliminate some of these techniques. But actually, I think that even implementing cookie in object header will not change situation a lot, because if we take a look at iOS, Apple iOS, or Linux, there are exploit writers use several vulnerabilities. For example, information leakage to leak value of cookie and then implement some of the techniques. So, but basically, Microsoft should implement cookie to eliminate these very easy techniques. So, any questions?
Anyone have any questions for Nikita?
It's scary to be the first question after such a... So that structure of objects allocated in chunks,
Yep.
together with their constructor, destructor, this is essentially the KMEM, or the slab allocator, right?
Well, kind of.
It's so, Linux has that, Solaris has that. Solaris has a lot of that because they are sort of the object-oriented kernel. So would you say that the entire idea of storing objects with their vtables and ops methods is a bad thing?
Yeah, well, actually, I haven't tested, but this idea should work on every operating system.
Right.
Because there are I think almost operating systems use kernel objects. So, but it depends on some tricks, because to apply to not trigger blue screen, there is a trick in Windows kernel. We have to make a hole to predict that allocation will take place at the bottom. So if we if we construct page in such ways that allocation will take place in the middle or in the top, there will be blue screen. So actually, this idea should work on every operating system, but implementation, depends on allocator mechanisms of operating system.
Right. But generally, I interpret your fix recommendation as saying, whenever you allocate objects, put in some extra context, just like cookies or object headers or anything like that. Without that, any slab-based memory allocation, any KMEM, any VMEM memory allocation would be susceptible to this.
So, so what's the question? Sorry.
Will cookies help?
Just a little bit. Well, if you set, basically, I have another, reset to change this value, bad bobo, to something like on the top of address space, like FFFFFF, because basically, if you take a look of contents of this array, there are zeros, so zeros you can't allocate null page on Windows 8, and if Microsoft changes bad Bobo constant, this idea will die. So, but cookie will help a little bit, in my opinion. But and Microsoft should change this magic value.
Thank you.
Any other questions? No? All right, well, Nikita, thank you very much for your talk.